So greetings of the day, everyone. It's absolutely a pleasure to be talking to you once again in this webinar, which is on a particular aspect of GPR as part of SUE, that is utility mapping. And today we are going to talk about the role which step frequency radar is making in the entire scenario of utility mapping. Now, this is very exciting for me, and I am actually very excited about this webinar for three reasons. First is that I did my first project of GPR somewhere in 1996 in India for utilities mapping. So 25 years, a long time since the time I've been working with GPR. So that really makes me excited every time I'm talking about this particular technology. In 2001, I started the concept of subsurface utility engineering, at least in Indian market, because there were a lot of frustrations with the use of only GPR for utility mapping, and that's how SUE was brought in, and that was in 2001. So again, around 20 years back. So every time I'm talking of utility mapping, it really excites me. So these two reasons, GPR and utility mapping coming together. And third reason I'll be telling you during the presentation, maybe in the first or second slide itself. All right, so without any further introductions, let's start with the presentation for today. I'm going to share my screen. Right. And I'll need a quick confirmation from our IT partner, Rashid ji. Everything is fine?
All good, sir.
Good. So today's webinar is on step frequency continuous wave ground penetrating radar, SFCW, what we call in short, a paradigm shift in utility mapping. And technology partner is Screening Eagle and PROCEQ, and this webinar is being presented by AF Academy. And this is a third reason why I'm so excited about this webinar. Last I checked, there are around 700 participants from 67 countries around the world. So it's really exciting to be sharing ideas with all of you, learning from all of you based on your experiences and taking it forward. So thank you very much once again for joining from practically all parts of the world. And it's really very exciting. Session guidelines are very, very simple. We will take questions in the chat box. You can keep putting the questions in the chat box as we go forward. We have with us Dr. Maria and Mr. Augustine. Both are with Screening Eagle, and they have their extensive experience with SFCW. So your questions mostly will be answered in the chat box at the same time. So please keep putting your questions in the chat box, but I will come towards the end of the session to take whatever questions are remaining. And that's basically the only guideline. And then about very brief introduction about AF Academy. This is the organization which provides training and knowledge sharing platform to decision and policy makers, working professionals, operating level personnel, and aspiring students willing to specialize in technical sectors through medium of training and courses. And this is the website afacademy.org, where you can go and see the details of various offered online courses. Just a very brief glimpse, the Academy is having courses on GPR, then advanced course on GPR, having the courses on dam geophysics, on dam and network safety assurance. And over the last 2 or 3 months, 4 new courses have been added, including on cross-hole seismic test, downhole seismic test and cross-hole seismic tomography, electrical raise duty imaging, MASW, and seismic diffraction. So these are the latest courses. As I said, all the details you can find on the Academy website, afacademy.org. The technology partner for this particular webinar are PROCEQ, Screening Eagle, basically, which has come in existence with handshaking of PROCEQ, which is a leading NDT manufacturer since 1954, and DreamLab, which is into software and robotics since 2015. And they have come together, and Screening Eagle is the organization which is having more than 200 employees in 8 country offices, 3 R&D sites, more than 200 distributors in more than 100 countries. So this is the technology partner for this particular webinar. They have a global network, as you can see the footprints in the map of the world. A very brief introduction about myself. I'm a professional geophysicist. I'm working in the field of near surface geophysics for last 31 years. I started my career as a logging geophysicist, then went on to work for a brief period with atomic energy, where we were looking for uranium. And then I started a full-fledged company in the field of near-surface geophysics. I'm also chairman of AF Academy, which is bringing you this webinar, and the managing director of Parson, which is the engineering geophysics company which I have. I graduated in 1990 as gold medalist in MTech Applied Geophysics from University of Roorkee, which is now known as IIT Roorkee. And since then, I'm working on various fields, including development of codes and practices, training programs. Now, when it comes to underground utility mapping, 1996 was the first commercial use of GPR in India, where I was the lead geophysicist for a Delhi Metro project from the Indian side. So 1996 is the time when we pioneered use of GPR in India. I've practically worked with most of the available models of GPR in around 18 countries around the world. Even the first ever city utility mapping project was done by me in 1999. And since then, we have been working on various cities, various countries. The concept of SUE was introduced in 2001 by me. And since then, SUE has become a part of major projects in the country. I'm also the principal author of Indian Code or Standard for Subsurface Utility Engineering, which we brought out in 2018 in India. Earlier, we had international standards. We had ASC 3802, we had PASS, but we didn't have a standard in India, which was brought out in 2018. All right. So now coming to the topic of the day, that is subsurface utilities and managing these. Now, if you really look at the underground infrastructure, it looks something like this. So it's practically a jungle of utilities down there. And the footprint of this new construction, repair, or remediation often conflict with existing infrastructure. So whenever you're going for a new project, it can be just putting a pile for a bridge. It can be taking a tunnel for the metro. It can be anything which you are doing on the ground. When we start excavating, that's where we come in conflict with this existing infrastructure. So this is mostly detected in the construction phase. This is a story which is common world over. I don't need to elaborate any further on this. Now, the problem is that cost of conflict resolution and potential for catastrophic damages are the highest at this stage. Because what has happened is you have already planned your activity. You have decided that this is where, let's say, I'm going to put my foot of the bridge, or this is the route which I'm going to take for my tunnel or my pipeline or whatever, right? Your machinery is there, your plan is finalized, your construction crew is there. And as you start doing it, suddenly you come across the existing utilities. Now, that's a big problem because it will either mean shifting of the existing utilities or change of your plan, which means everything will be set off by a particular period of time. So what we call time delays and cost overruns, etc., etc. And catastrophic damages that you don't know about a utility. You are using a heavy machinery there and suddenly you hit a high tension electrical cable, or you hit a gas pipeline, or you hit a water pipeline. Now, these accidents are something, again, I don't need to tell you because in newspapers, they come very nicely. Every time it happens, they're really flashed across the newspapers, and it really, gives pretty bad name to whichever infrastructure company is involved in that project. So if you really look at a typical phase, a design phase, what happens is that there is a guy who is, there are two people rather, they're on the desk. One is saying, I think the gas line is here, but I'm not really sure. It might be in conflict with this proposed piling. All right. So he is trying to use his brain and say, I think it might be there. Other guy says, I guess we'll let the contractor worry about that. Fact is that contractor doesn't worry about it. Now, there have been so many cases, like one particular case I always quote because that happened right when I was going through this process of SUE, that there was a flyover in Surat. It was opened for public, and just 3 days later, it collapsed because one of the footing was right over a receiver line, and it simply gave in. So what happened? Contractor said, I made it as per the drawing given to me by the consultant. Consultant said, I made the drawing based on the utility information given to me by the client. So ultimately, no one was answerable. Okay, so it makes it extremely difficult to manage the risks that are created by existing underground utilities. So we practically take most of our design situations in urban projects with our eyes closed because we don't have this data. So are we a smart decision maker? Definitely we are not. So what is a solution? Now, solution comes in the form of SUE, subsurface utility engineering, which involves new technologies for solutions, that is surface geophysics, surveying techniques, CAD and GIS, minimally intrusive excavation, and then convergence and systematic use of this data. That is what we call SUE. Now, this particular webinar is definitely not about SUE. I just wanted to give a very brief introduction to this. I will just put my timer, just excuse me, because I don't want to overshoot the time. So I'll just put a timer for myself. Sorry. All right. Because I always want to give enough time for question and answer towards the end of the session. And these topics are such that if you start discussing, you can keep doing it endlessly. All right, now I have a timer, so I know how much time I am consuming. Perfect. So this is what SUE is. And as I said, this is not a webinar on SUE. If anyone of you is interested in more details of SUE, please write to us. We just conducted a full webinar on SUE that was almost 1 hour webinar. We would be happy to share with you recording of that webinar, so please go through it. This particular webinar is more focused on use of a particular type of GPR for utility mapping. But I found it very, very important to give you a brief introduction to SUE so that no one goes back with the notion that GPR is all we need for utility mapping. Now, that's the worst notion one can have. And I do not really want to pass across that message. And that's why if once it comes to utility mapping, the right process is SUE, subsurface utility mapping. And what it does that it breaks down the entire information into quality levels. So once you look at the map which has been prepared using the procedure of SUE, every utility has a quality level associated with that. And that quality level tells you what is the reliability of that information. So for example, quality level D, this is the least reliable level. It is information gathered solely from existing utility records. So this is what was conventionally done. Whenever a project was conceived, they will try to get whatever information is with utility owners and put that in a composite, and that was quality level D. Extremely inaccurate and the least reliable information, but very useful at one particular phase of the project. I will tell you where we can use different type of information. Then comes quality level C, which involves surveying visible above ground utility facilities and correlation this information with existing utility records. So this is where you take your land surveyors into the field, you look at the manholes, you look at the water walls, you look at the chambers, junction boxes, and then with that you try to make sense of how the utility is going. Now, world over, studies have shown that even with quality level C information, which was the last stage before SUE came in picture, around 40% is the omission rate. 40%. Now that's big. All right. So you cannot really afford to live with quality level C, but this is what was there till the time SUE came in picture. Now, quality level B is where the entire process deviates from what was traditional. So in quality level B, you use surface geophysical techniques to determine the existence and horizontal position of underground utilities using geophysical surveys. Okay, this is where it deviates from the tradition. And then comes quality level A, which employs non-destructive digging equipment at critical points to determine the precise horizontal and vertical position, as well as size and type of underground utilities. So even after QLB, it is not that you have 100%. No, it is not 100%. It is giving you an approximate vertical position, a fairly good horizontal position, but it is not giving you any information about the type, about the material of the pipe and even the size of the pipe, etc. For that, you have to go to quality level A. This gives you a guarantee in 3D, as they call it. Okay. Now, how does it work? SUE does not follow any set pattern. So it can be project specific, depending on what is the need of the project. For example, you're in a very initial phase of planning. For that, you can have quality level D information, because you just want to know in this particular stretch, what all different utility owners have the utilities there. All right, quality level D information is good enough. You really don't have to go for quality level A. Preliminary design, you can go for quality level B. But once it comes to final design and construction, of course, you should go to quality level A and then go towards construction. So this is basically how the SUE flows. Now, quality level B is the first level where subsurface utility data departs from traditional practices. It involves supplementing quality level D information with designating, surveying, and mapping. And this is where we use surface geophysical techniques to determine the existence of underground utilities in plan view. Now, use of this information allows decisions to be made during the preliminary design phase of a project in order to avoid conflict with the existing utilities. And of course, you can make slight adjustments. Now, there are different methods which are again involved in quality level B. Very important to note this point. First of all, when it comes to utility mapping, it is the entire process of SUE which should be followed right from quality level D to C to B to A. That's number one, point number one. Point number two, even in quality level B, there are different tools which are used for underground utility mapping. If you go to, for example, AC 3802, I think they mention some, 17, 18 different kind of geophysical methods, but the fact remains that that is more of theoretical discussion. In practice, if you look at it, GPR, induction locators, gas pipe locators, and acoustic locators. These four basically make the toolkit which is used in quality level B information, right? So you have induction locator here, you have GPR here, you have gas pipe locator and acoustic locators. These are the tools. As I said, I'm not going in details of these tools, but in this PPT itself, I have put the links. So for example, you have a link here. All right, so you can go for induction locator if you want more details about it. For acoustic locators, you can go for this link. For gas pipeline locator, you can go for this link. So all the methods which we are going to talk when we talk about in SUE, you have very good information which is available in public domain. I have put the links here. Today, I'm going to talk more about GPR, ground penetrating radar. So this was just a small introduction, which I felt is mandatory, because many a times after a session of GPR for utility mapping, I've seen people going home with a notion that, all right, if it comes to utility mapping, we just need GPR. That's not the right notion. And I really want to make it clear from the beginning. So remember, ground penetrating radar is one of the important tools in the process of utility mapping. No single tool is a complete solution. The complete solution is subsurface utility engineering. So now in GPR, as I said, I've been using it for last 25 years now, and different models. Now different models have different central frequency antennas, right? So traditionally used frequencies, the commonly used frequencies in the traditional GPR survey is 100 megahertz to 500 megahertz. Now, when I say 100 megahertz, there might be one manufacturer which is having 150 megahertz. When I say 500, there might be one manufacturer which has 450. But generally, this is the commonly used range of frequencies, 100 megahertz to 500 central frequencies. Okay, I will come to the concept of central frequencies. So this is generally the antennas which I use. Grid survey is required because utilities can be going in any direction, right? So they can be going parallel to the road and perpendicular to the road. And we know that we detect the utility when we go across it. So grid survey is generally required. Mostly you use either single channel equipment, or these days you have got array type of equipment, which are pretty big, which is array of antennas, and you can use that. You can do 2D processing or 3D processing, depending on whether it is single channel or array type equipment. Even in single channel, if you do good dense data acquisition, you can do 3D processing. In very complex areas, for example, we are working in airports where sometimes there's practically utility jungle, we go for 3D processing in that case. This is the survey grid. Again, I have not put any numbers here. It completely depends on what is the type of utility you're following and what is the distance in which you can imagine a deviation. So for example, if a pipe is going in this direction, you can do these lines even every 10 meters or 20 meters, depending on what is the deviation you're expecting. When you come near to a junction, you want to see how the utility is going in one direction or other, so the grid becomes slightly dense. Okay, so this is how the work is generally carried out. And this is a picture. This is not my picture. I've borrowed it from somewhere, where they show GPR that it detects everything, right? So it detects water line, communication line, gas, sewer, etc., etc. So they say it detects them all. What I just add there is within technological limitations. Okay, the GPR is extremely dependent on the soil condition, the size of the utility versus the depth of the utility. So a utility at a particular depth may be very visible, but the same utility when it goes down, it might not be visible at all. So within the technological limitations, yes, this is a fact that GPR is the technology which can detect both metallic and non-metallic utilities. For example, if you talk about induction locator, now induction locator will only work on metallic, right? Either the cables or the metallic pipes, etc., etc. If you want to detect a non-metallic, for example, Siebel line, you have to put a sonde inside that, which becomes the emitter, transmitter. Okay, so GPR is the tool which can detect all type of utilities. So that way, this representation is fine, but within the technological limitations. Very important to note. And how do we do it? Is that we basically do the GPR line, and then we look for the hyperbolas, and we look at the similar character of hyperbola, similar depth of hyperbola, and then we say line 1, line 2, line 3, line 4, line 5. We have got this hyperbola, which is of the similar character and at the similar depth. So we join these together to make a utility. So something like this. You have number of lines. So this is same character, same depth. So this will become one utility, this will become second, and this will become third, like this. So this is how the entire interpretation goes when we are using 2D work with GPR. So this is how we track the linear utilities. Okay, so 1, 2, 3, 4, and then we plot it. Now these days you can plot it manually. You can directly sometimes export data from your software to the CAD drawing, etc., etc. These are the software interventions which are taking place. Now types of GPR. So in types of GPR, we have time domain GPR and we have frequency domain GPR. Okay, so again, we have broadband pulse, noise modulated, we have FMCW, we have SFCW. Okay, frequency modulated, step frequency, continuous wave. So these are two broad categories: time domain and frequency domain. So GPR, so these are the categories where it falls. Now, time domain is using short EM impulses. All right, so we are sending electromagnetic impulses at a particular interval. So in a 1 second, for example, you might be sending 80 impulses or even more than that or less than that, depending on which equipment you are using. Now these impulses are going inside, getting reflected from wherever there is a change in dielectric constant, and you are doing the entire measurement in time domain. Now the second class uses sinusoidal waves that sweep over a range of frequencies and are known as step frequency or continuous wave radar system. Now, this is the second one where we are using a range of frequencies. So, for example, you can have a complete range of, let's say, 40 megahertz to 3,500 megahertz. And and system is sweeping over this entire range of frequencies. Now, this is called step frequency or continuous wave radar system. Till date, most of the commercial GPR systems which we have been using, even I have been using till recently, are impulse radar systems. Okay, so whatever names I have told you, or you might be familiar with, the GSSI, MALA, IDS, ZOND, whatever, like most of these names of GPR which we talk about are impulse radar systems. Okay, so they look something like this. Again, there are varieties there. So you have single frequency GPR. This is a single frequency. You have dual frequency GPR. So in the same GPR, you practically are having two frequencies. This is very, very common these days. Okay. Then you have multi-channel GPR. So as I said, this is an array of antennas. So here is a module in which this complete array of receiver and transmitter is there. So once you sweep with this, again, you are getting almost a continuous picture of the subsurface. You don't have to do, crossed lines and longitudinal lines. You can just do one swath and you will get the image of your subsurface. So this is multi-channel GPR. Very good, very effective. Only problem is the accessibility. That is when you're working in narrow areas or on the footpath, etc., etc. Practical application becomes slightly difficult. And then we have come up with the concept of HDR antennas, okay, high dynamic range antennas, where the bandwidth is much larger and obviously the signal strength becomes much better. So I have started using SDR antennas for last around 6-7 years now, and definitely they give much better performance compared to earlier antennas which we were using. Now, there are certain limitations of GPR, and whenever I was talking of GPR to any audience, I always used to tell them that, look, first of all, GPR is highly dependent on soil conditions. Now, that is a fact. In certain cases, GPR can be very, very effective, and certain cases, GPR can be completely useless. All right. For example, you put it on seawater, you won't see anything. You put it on highly saturated clays with very high conductivity, you will not see anything. You put it on ice, wonderful. You are seeing up to hundreds of meters. You put it on solid granite, you are seeing up to 50s and hundreds of meters. So soil conditions, especially the conductivity, the homogeneity, it affects the result tremendously. Now that's not in our control, all right? The second part was that there was always a compromise between what we call depth and resolution. What it means is that if we are using high frequency will be able to resolve targets which are very small, okay, small targets, but the depth of penetration will be limited. When we use low frequency, we will be able to see deeper, but resolution will be compromised. So in GPR, even today, when we use it, like I have got around 10 or 12 teams who are using GPR practically every day, covering almost 15 to 20 kilometers a day. And I look at that data. We practically end up using 2 to 3 antennas for every project, because we need, let's say, 500 megahertz antenna for high resolution mapping. Then we need 300 megahertz antenna for intermediate depth mapping, and 100 megahertz antenna for very deep mapping, right? So multiple antennas need to be used to achieve the target. Now, this is one of the things which is there in time domain GPR, which no one can question, that has been there. So penetration, depth, and resolution are inversely proportional, okay? More penetration depth means lesser resolution. Lesser penetration depth means higher resolution, okay? It's based on frequency. And then I came across this step frequency continuous wave GPR concept, which I saw first video or first information somewhere on LinkedIn. I was excited about it. And finally, I was able to get my hands on one system, which now I have been using it for some time. And that is what excites me to share the results with you. So this is GS8000. This is one solution for locating objects and mapping the underground world using SFCW GPR. Superior clarity of data, accurately georeference, adapts to different terrains and application, access to your data from anywhere, anytime. All this I'll be covering. Applications obviously involve utility strike prevention, SUE, asset inspection, bridges, asphalt, geophysical investigation, archaeology, forensics. So as we know, GPR has so many applications, but today we are going to focus on utility mapping. Okay.
Often
this is
we
one
just
small
don't
video
know. But what
I like to play so that you can have a feel of this system.
Often we just don't know. But what if we did? Then we could predict chronic defects of aging infrastructure, a problem that requires massive investments. This insight is now possible with the new PROCEQ GS8000, the universal ground-penetrating radar solution for subsurface locating and mapping. Compact and portable, it is ready to go within a few seconds. Thanks to its unique radar technology, GS8000 is able to see even small objects and defects within structures while seeing deeply at the same time. Designed to be flexible, GS8000 adapts to different ground conditions with ease. With a comprehensive collection of on-site capabilities, even the most complex conditions can be mapped during geophysical and forensic investigations. Every few seconds, somewhere in the world, a utility line is hit during construction, causing service disruptions and compromising safety. Equipped with a plug-and-play positioning system with centimeter accuracy and artificial intelligence, GS8000 not only locates the safe place to dig, but also accurately detects utilities on the fly, visualizing in the most intuitive way what otherwise cannot be seen and makes our cities truly smart. Locating objects and mapping the underground world using GPR with one device and with all required frequencies for any terrain and for all users. Powered by software that continuously evolves, making sure your investments stay up to date. GS8000 is all of these, and will be much more.
Now, I love this part, when you can hold your tab, and this is the iPad, and you can actually put it on the ground and you can see where the utilities are under the ground. And initially I thought, is it just a marketing video? Like, does it really happen like this? This is called augmented reality. And then when I got my own system and I did this, like it actually is beautiful, because once you have done the data collection, like within 5 minutes of finishing your data collection, you can actually put your device on the road and see where the utilities are going. So practically you're not marking the utilities on road anymore, because you are able to see it right there. Very interesting and very imaginative. All right, now when we talk about journey of digital transformation, like GPR locating, and then of course you can have digitization and GPR locating coupled with the GNSS surveying, the integration of the two, and then is coming making use of the modern technology to actually create the data in real time, and that is and use the data for subsurface utility engineering. So this is a complete journey of digital transformation, which I'm able to experience with this system. So if you really look at it, it combines SFCW, GPR, and high accuracy GNSS positioning. So you pretty compact. You have this. This is the entire system, and this is your GNSS receiver, and this is the entire bandwidth of frequency, which I'll be discussing about. And right once we are doing the work, we are able to see the results on the screen right there, including all the processing steps which are incorporated, like be it gain, linear or time gain, background removal, different colors, filtering options, etc., etc. So we really don't need to bring the data back home for further processing or anything. The entire processing can be done real time right there, and results can be seen there. So that's what really excited me a lot. So if you look at the Pulse GPR and SFCW, the major difference when we talk about. So SFCW in Pulse radar, as I just discussed, you want high resolution images, small utilities to be detected, use a high frequency antenna. You will have the limitation of your depth of penetration, but it will give you data with high resolution. Now you want to go deeper, use a low frequency antenna. It will not be able to give you very, very high resolution, but you'll be able to go deeper. But when it comes to SFCW, GPR, since we are having the frequency, which is practically ranging from something like 40 megahertz to something like 4,000 megahertz, you are having the very, very high frequency component for near surface high resolution mapping. And you also have low frequency component for the deep mapping of deeper utilities. Okay, now that is what you can say is a major change when it comes to a paradigm shift when it comes to utility mapping, that with this kind of system, the need to have different antennas is definitely removed. Now that's just from a user perspective. Going slightly deeper into it, if you look at the data, definitely the noise is much more reduced. The data clarity is much more better, which we will just see in slides to come. So this was a Pulse GPR dilemma. Choose a central frequency. So for example, central frequency is 250. And now coming to that discussion. When we say central frequency, so central frequency does not mean that it is the only frequency. Okay, it is where your amplitude spectrum is peaking. Practically a 270 megahertz antenna will have, let's say 500 megahertz antenna will have something around 250 to 750. So that is the kind of range you are going to have. But your peak power will be centered in the central frequency, and that is why we always refer to the central frequency. So in Pulse GPR, for example, you have 270. So this is going to be your frequency. Then again, let's say close to 500. This is going to be a frequency. So you need to decide what all frequencies you are going to use to maybe take care of the complete spectrum from here to here. And then, of course, you go to, let's say, concrete inspection. So again, you have different structures, you have different system, 1.5 gigahertz, 2 gigahertz, etc., etc. So this is how, because in utilities, as we know, we have system right from 250 up to 750, even 900. Like I use 900 sometime for very, very, shallow information. So that's the spectrum for utilities. And then a totally different spectrum for structures, because there we are looking for very small objects like reinforcement bars, small interfaces in the layers, asphalt layer, etc., etc. So it comes a different radar system for structures. This was the pulse GPR dilemma, that to choose to actually cover the entire frequency spectrum, you need number of these frequencies. And what happens when we use SFCW? The entire frequency spectrum, this entire frequency spectrum is being covered with a single antenna. So all frequency spectrum covered in 2 milliseconds. Now that is where a major shift has taken place in a way, all right, that you are having now the complete spectrum being covered with one antenna, one equipment. So this is a small case study where the differences have been studied based on various GPR models, and they are all reputed GPR models. And this is GSSI UTT scan 350 megahertz is A, then IDS Opera Duo B and C, that is 300 and 700 megahertz. And then is the PROCEQ is 40 to 960 is the low frequency component, and 40 to 3440 is the high frequency component. And by the way, they are listed separately, but both the things are in the single antenna, and the results also come on a single screen. You can obviously divide the files later for your internal analysis purpose, but when you're seeing it on the screen, you actually see both the frequencies together. So you can, shift the window and look at the shallow part with the high frequency and the deeper part with the low frequency. So that's a beautiful thing which is there. Anyway, coming to this particular comparison. So this was one area which was scanned, and this area was having basically three major parts. One was simple utility scenario, then next was civil structure. So it was a bridge, and then was complex utility scenario. All right. So again, going back here, 1A is GSSI, B is IDS 300, C is IDS 700, and D and E are PROCEQ. And now let's look at the results. Okay. So this is zone 1, simple utility scenario. All right. So if you see here, this is from GSSI, this is from IDS 300, IDS 700, and this is coming from PROCEQ low frequency and PROCEQ high frequency. Now, just by looking at this, it becomes very, very clear that there are, for example, small things, small feature here, which is coming here, all right, which is coming here. It is really not coming in this. Then look at this feature, all right, this feature, this utility hyperbola is being cut by another hyperbola here, all right. Now, this feature, if you look, we are not able to get it, all right, because it is 300 megahertz. So 300 megahertz will definitely have an issue when it comes to very, very high resolution. Now you look at it, what we see actually on the screen is something like this. That is on top part, you see coming from the high frequency, you can adjust this bar. You can take this bar completely up, so you will see completely low frequency information. But if you are interested in high frequency definition, look here. And you can see the resolution, the change in the resolution. Each and every part of the radargram becomes very, very high resolution when we are working with high frequency. And same clarity and definition of each feature, lessening of the noise, that is what becomes very, very apparent quickly when we do the comparison of impulse radar with the SFCW. Now let's go to the next part of it. Now next part is when we are talking about the concrete structure. Okay, so here in 300 megahertz GSSI, of course, you can't see any definition of rebars. Understood? You can't, for the simple reason that it is it is low frequency. It will not give resolution on that rebar part of it. For that, you should be using GSSI concrete scan, which is around 1.5 gigahertz or 2 gigahertz, right? Then again, same in the IDS, the top definition is missing. Okay, now here you are having the definition, but you will not have too much of deeper information. And then D and C. Okay, look at this one, very high frequency, and once you zoom this, you are able to look the complete hyperbolas and all other definitions of the structures very, very clearly, much more clearly compared to any of the systems. And in this, since the frequency, again, as I said, is ranging from 40 to, let's say, 4000, you're practically having this high definition on the top and in the information from the deeper part also. Now, this is another complex utility scenario where there are a number of utilities close to each other. And this is again 300, and this is 350, this is 700. And look, once we come to 700, resolution is improving, but you're almost missing this particular part. That is, even if it was slightly deeper, you're going to miss it. And see low frequency and the high frequency of GS 8000, where you are able to see very high resolution in the shallower part and deep information based on the low frequency. This is what we are discussing. This particular detailing will come if you are using something around 900 or 1.5 gigahertz or 2 gigahertz antenna, depending obviously on the soil conditions. Okay, this is not possible by any equipment which is used for utility mapping. This is not possible by any equipment which is used for utility mapping. Okay, this is something which only comes when you use a GPR which is there for structural mapping. Okay, but in this, you have high resolution which is equivalent to the structural mapping, and you have the depth and details for the deeper one. And of course, you can see how different objects are very, very clear, how the noise is practically absent in the SFCW record. There's practically no noise in the record. Okay, so this is a very good example I wanted to show you. And now, now here you will basically see the strength of the area scan. Okay, when we say area scan, you're working in a particular area. So what you can do is you can set your grid. Okay, you give the x-axis, the difference between the lines, etc., etc. And this is the grid which you have set. And now you go on the site, and intuitively it will tell you how you are moving. Okay, so how you are moving, and like this, you keep doing the lines in one direction, and then you do the lines in the other direction. Okay. So one direction is over. Now he is doing in the other direction like this. Okay. And this is real time. This kind of depth slice is real time. Okay. So no processing is being done later. What you see on the iPad right now is the real time how you see it. You see the A scan and you see these depth slices. All right. And you can move from here. You can move this to determine what depth I want to see. And once you see a linear object, you can mark it. You can mark the linear object, okay, and then even define it, that whether it is a water line, whether it is a sewer line, etc. If you have, and this is the augmented reality. You put this marker on the bottom left of the grid, and then you will be able to see as if you are making the ground transparent. This is real time. All right. No processing has been done for this. This is real time. Now, that really makes it extremely effective to take decisions right on the site if you want to, okay, to make people understand what utilities are going in what direction. Of course, then you can export it in VXF, you can share it with anyone sitting in any part of the world. Since you have a GNSS receiver, very high accuracy GNSS receiver, you can directly put it on Google Earth and able to visualize it. And this data sharing also takes place in the real time. That is, whatever data is there through the workspace, your person sitting in the headquarters can look at the data. So it's like being your most experienced geophysicist being there right on the site. That is what enables, because you cannot have, for example, 10 geophysicists with 20 years of experience. You can have a lot of young geophysicists. They can be on site. They can be sharing the data with the headquarters, which is happening in my case today. My guys are taking data right now in Karnataka, and they are sharing the data with me. And me sharing is not by email, etc., etc. I am able to see the data in real time as it is happening there. Okay, that's a big advantage. Now, this is another example of a beautiful definition of a trench and a pipe inside the trench, okay, apart from other things. So there are a few examples which I wanted to show you. This is another example of this metal pipe. So this line obviously has gone over a metal pipe, and these are two non-metallic pipes beautifully. So look at the definition and lack of noise in the entire thing. That is what And this is the high frequency part of it. As I said, screen is splitted with high frequency and low frequency in the, so you can just have to slide this. So when you looked at high frequency, very clear definition of near surface features, and then low frequency for much deeper features. Now, this is what we are looking at. This for concrete sewer conduits, very clearly visible, top and bottom part of it. Okay, number of such examples. I am slightly running short on time, and ultimately this is the best part of it. Once you finish the work, you can look at your take your iPad, put it right on the surface on the ground, and actually look at what is going inside. Quick decision making it allows. Now, this is a very good example of a array type system. So these array type system, definitely these are very, very expensive systems, and you have this data. And this is the data which has been obtained from this PROCEQ GS800, and you can see it is very comparable, even to me more clearer for that matter, with the very expensive array type system. So the journey of digital transformation, if we talk about, this is the complete data which is being taken, okay, and then it is shared with Inspect, can go to Autodesk, Google Earth Report, and then GPR slice for processing, further processing if it is required. And ultimately, you can have the complete BIM deliverables in real 3D. And as I'm told, the new ASC 3802, which has been revised, is referring to BIM deliverables as part of SUV report. So this entire digital transformation makes that happen. Okay. Now, what is next? The soon is free path scanning. Now, as of now, we are generally doing the scanning in the grid. Okay. If we are able to do free path scanning without really following a particular grid pattern, things become that much faster. So that's something which is coming up. Guided grid scanning, then benefits from this data: 60 minutes data collection, 30 minutes of processing with GPR slice, 5-kilometer walk, one single cloud shared file, 0 interruption in the workflow. And this is the complete data which has been obtained in this much of time and effort. So it makes the things that much faster, because we all know in utility mapping, we really, obviously it is a time taking process. Whatever time is taken in data acquisition, almost equivalent or almost double the time is taken in data processing and report preparation, which is getting automated through this process. So high precision detection of underground utilities, representation in almost 3D. This is again data which I collected very close to my office. Difference in my typical impulse radar system and SFCW. Now this is the data of typical radar impulse radar system. You know, we are able to see the utility, no problem. We are able to see utilities. We are also able to see some kind of disturbance in the subsurface. What it is, I'm not really sure. There is of course ringing in the data. And then this is the data from SFCW. You can see the same signatures are much more clearer with much less noise, and the trench definition is also much better in this particular case. This is same in the, and I have not done any filtering on this data. This is practically the raw data. Okay, so no filtering has been done on this data. And once we go to the high frequency component of this, as you can see, this is 50 nanoseconds. High frequency component, I'm going for 20 nanoseconds only. And now you can see near surface layering with great clarity. Of course, the utilities are there. They have not gone anywhere, but now the layering is become much more clear with this. If I do a little bit of processing on this, just to highlight the horizontal reflectors, it will give me the layer-based data very nicely, which practically is not obtained in any of the GPR which we use only for utility mapping, and that's a fact. Okay. If we need layer-based data, which we are working a lot on airports and roads and highways, we are using high frequency, like we are using 900 or 1.5 gigahertz, not the one which we use for utility mapping. But here you have a combination of high frequency and low frequency in the single system, and you get this. Okay, next comes advanced software and cloud computing, which is the biggest advantage. First is the data is securely saved on the cloud, so that if the iPad is lost or damaged, the data is not lost, because all this data is being recorded. iPad is your interface. It's a wireless system. So you have this antenna and then you have this iPad, they are wirelessly connected, including a GNSS, and entire thing is being recorded in this iPad. And this is saved on the cloud. So even if you lose the iPad because of whatever reason or damage, your data is saved. And then you can simply log in from any iPad around the world and your data is there. Okay, so that's what I said, that, you know, I have my data acquisition going on in Kerala or Karnataka, and sitting here, I just have to log in my system and I have access to the complete data which is being acquired there. Okay, so you don't need to, you know, back up on USB, pen drive, data transfer, etc., etc. Okay, collaboration is very easy. You can share data with the click of a button, share URL, and a colleague can open the data on the other side of the world. They can edit the data, change the game, filters, etc., and then send it back to you. This is useful when an expert is not available on site and the inspector needs report. So that's what I was saying, that you can't send expert everywhere, right? So even if one expert is sitting in office and 10 of these your people are working in different parts of the world or country, this expert can guide all of them at the same time. Okay, this is what collaboration is. So collaboration becomes that much easier. Workspace makes it really easy to review your data, extract images for report, etc., etc., from the comfort of your desk. Workspace can be used on any internet browser in any platform, be it Android, iPhone, iPad, desktop, PC, laptop, etc. So from there, you can extract the images, you can put them in the report. So everything is seamless. So it's one good example that, you know, some data was being collected in Singapore. And so this is what data was being collected in Singapore. He placed it on his image, and then he sent this data to Switzerland, and the expert was able to put it on the Google Earth sitting in Switzerland and look at the data. So this is how the seamless collaboration and the flow of data can take place from one office to the other. So practically, this is what I see as the future. All right, like a beautiful robot taking care of all the GPR work. When we geophysicists finally, or engineers, can finally relax and just press few buttons to do it. All right, so this is what I wanted to present today on SFCW GPR for utility mapping. And I would really like to thank you for your patient hearing. For any equipment related inquiry, you can directly contact Mr. Augustine Zhang at info-ac@screeningeagle.com. For any technical question you might have on GPR, please feel free to write to me. This is my number, sanjay@parson.biz. And after this, we will